Time for another lecture. This one we're going to be talking about the sun, and next lecture we're also talking about the sun some more. That would be the end of the first part of the course. You'll have an exam, and then the next part of the course we're going to keep talking about stars for a while. So the sun, if you didn't know, is a star. Like a number of other stars that you see in the night sky, it just so happens to be the one that we're revolving around. Now this image is pretty nice. It could be kind of confusing though, because you don't see hardly any of this kind of thing when we look at the sun. For one, this is a composite of two different images where the yellow ball with a lot going on in the middle, that's the sun, but it's not in a normal visible wavelength. I think it's probably in a very far UV or extreme UV, maybe even X-ray. And that's one image here. In the background of that, you have this black disk. And this is something that astronomers do in order to check out the atmosphere of the sun, or like see the outer kind of area, volume of the sun. Because if you look at the sun, then you're pretty much just blinded by one part of what makes it the sun. Right? It's called the photosphere. We'll talk more about that. Right? But when you look at the sun, that part of the sun, that layer of the sun is so bright that you don't see anything else. However, if you put this disk over, sometimes called an occulting disk that's covering up the sun, you block all that light from coming straight at you, then you can maybe start to see some of the things that are happening around the edges of the sun, sort of upper atmosphere of the sun. So that's the background image. You have this black disk over this actual sun, which allows us to see some of the activity going on in the upper atmosphere of the sun. And these sort of plumes, or maybe even jet-looking kind of things. As it turns out, after looking around at a bunch of different stars, many different stars, we found that our sun is pretty average. In terms of size, it's kind of medium-ish size, not really big, not really small. In terms of its age, it's not really super old, it's not really young. And in terms of its temperature, it's not a super hot star, it's not a very cold star, it's in the middle. It's kind of like a just right star for us. And if it wasn't just right, then we probably wouldn't be here to be asking why it's not just right. Alright, so just quickly look at this table of a number of different characteristics of the sun. So our mean distance, or average distance, 1 AU, 1 astronomical unit, which is about 150,000 kilometers. 150 million kilometers, sorry. Its mass, it is over 300,000 times the mass of the Earth. Very, very massive. The diameter of the photosphere, so to that layer out of the sun, which I mentioned is sort of like the visible layer of the sun that we see most often when we look, at least in visible light, is about 100 Earth diameters, maybe closer to 110 Earth diameters. Its density, you can see 1.41 grams per cubic centimeter, which, if you think back to the planets, is kind of similar to Jupiter. And actually, I think the other giant planets too, except for Saturn. Saturn's even less dense. If you were on the surface, the gravitational pull you would feel would be like 28 times that you feel on Earth. Right? You'd be like squished down to the surface. Well, if you didn't burn up already. There's other things on here, but we haven't really talked about some of them, and some of them will come to later, sort of like the spectral class I think we'll talk about later on. We talk more about stars in detail. The effective temperature is sort of the average temperature of its surface, the photosphere, about 5,800 Kelvin. The rotation period takes a little over 24 days, or closer to 25 days to rotate around. And just to mention that rotation, it's not as constant as the Earth's. It will vary, how long it actually takes to rotate fully around, up to 36 days. And being not solid, not every part of it is rotating the same rate. So the equator is rotating a little bit faster in general than more towards the poles. A nice little picture over there of the sun with the Earth to scale. See a little bit of comparison. The Earth is a pretty darn big thing from our perspective. It's this tiny little ball next to the sun now. Also in that picture is, I believe, what's called a prominence. This kind of loop of plasma coming out from the surface of the sun, going into its upper atmosphere. We'll get to some of that later. And then down the inset there is like a full picture of the sun. And again, that's not visible light. We don't see that when we look up at the sun. That is seeing more of the sort of atmosphere above that visible surface. I'm not sure what part of the spectrum that's actually in. It's either infrared or might actually be ultraviolet. Right, so we're going to be talking about the sun for a while, but very basically speaking, the sun is a gigantic ball of very, very hot gas. Pretty much it. Beyond that, the gas is so hot that atoms throughout most of the sun are not even able to hold themselves together. That means that electrons are pulled away from protons, and you end up with sort of this like soup of electrons and protons just kind of roaming around. In fact, that is one example of what we call a plasma. Now, unlike the gas giants, so Jupiter, I told you, like was almost a star, it almost reached nuclear fusion, but it did not. And so it still has that rocky core, didn't burn that up. The sun, however, seems like it just doesn't have any solid parts anywhere, right? It's all gas, some version of gas or plasma through and through. There do seem to be internal structures, like different layers inside of the sun, and we'll talk about those. But yeah, no solid surface or core. So look at here, the composition of the sun, 3/4 of it, almost 73%, is hydrogen. And about 25% is helium, right? And then just a couple of percent of other things. I think some carbon, some nitrogen, some of the more simple elements, low proton number elements. And for the most part, all the stuff in the sun is like single atoms. If you look around you, the sun on the Earth and what we're made up of is almost entirely built up of atoms combined together into what we call molecules. So multiple atoms together makes up a molecule, and those things build up to larger things. But in the sun, it's so hot that pretty much everything is just single atoms. There's no chemical bonds, there's no molecular structures. And in fact, the makeup of the sun, the fact that it's mostly hydrogen and helium, wasn't really accepted for quite a while. I believe the book mentions that it was actually the first woman who was allowed to get a PhD in astronomy that proposed this. I can't even say her name. Kapuskin? Not great. That was about 100 years ago, and was not accepted in her time, I believe. It wasn't until later that we were able to do some better measurements of the sun, and we finally had to accept that she was right. So this is an overview, a big picture of the layers, or like the structure of the sun overall. So there is what we would call the core, which is the center of the sun. It's not a solid thing like any of the planets. Also in the center of the sun is what we call this radiative zone, where electromagnetic energy, for the most part, is radiating outward. Outside of that is what we call the convection zone. And outside of that is this photosphere that I mentioned a couple of times. Right? So the photosphere is where most of the visible light from the sun comes, so that's generally what we see when we look at the sun. The photosphere is considered part of the Earth's atmosphere. It's sort of like the beginning of the Earth's atmosphere in a way. I don't know, the terminology is a little bit strange. So you go photosphere, and then chromosphere, which is another layer just outside this photosphere, and then finally outside of that is this corona. Corona is like upper atmosphere, and it goes way, way far out from the surface. So I think in this lecture, we're going to talk, for the most part now, about the sort of atmosphere of the sun, the stuff that we can actually see when we look at the sun, and that only goes down to this photosphere. It's difficult to pierce below the photosphere, and I think in the next lecture, we'll get to talking a bit more about what we think is going on in the inside with this core and this radiation zone, this convection zone. But for now, mostly the atmosphere of the sun. And like I said, that atmosphere, we say, starts at the photosphere, is that visible layer, sort of like a visible surface of the sun. Then you got the chromosphere, and then the corona. And these different layers are at different temperatures, and so they emit light at different wavelengths. Right? The photosphere is a certain temperature, so it emits light mostly in the visible range. The chromosphere is also emitting visible light, just not nearly as strongly as the photosphere, so we don't tend to see the chromosphere very much. The corona is surprisingly much hotter than the photosphere and the chromosphere. It gets incredibly hot, and so it emits in much shorter wavelengths, like X-rays and sort of extreme ultraviolet. Let's talk a little bit about the photosphere then. It's actually kind of difficult to get an image of what you would think of as the sun. And partly that's because like when you look up at the sun or when I look up at the sun, well, it's blinding for one thing. And you're generally looking at it through our atmosphere, maybe even through clouds, maybe even through a lot of the atmosphere when it's low on the horizon. The actual visualization of the sun, what you see, can vary, but when we try to go take a picture of it, we got to do it with some kind of technology, some cameras. It can be kind of tricky. So what I found, at least in the upper right, is an image taken with the white light. So I believe that means just the whole visible range. It was also called a true color image. At least in my mind, if I think of looking up the sun, in fact, for the most part, it just seems white. Very, very bright white. Unless it's during like a sunset or a sunrise, and that's because you're looking through a lot of atmosphere. So there you go, that's a picture of the sun. What are we seeing? What is that layer? That's the photosphere of the sun. Another image over here on the left, why it's a little bit more of that yellowish orange, I'm not exactly sure. Yeah. Anyway, also an image of the photosphere, and specifically in that image we can see these dark areas. Right? And these are what are known as sunspots. And then there's a little bit of a zoom in here where we see the sunspot a little more up closely. Also have a scale image of the Earth, or size of the Earth at least there. Kind of keep in mind just how large the sun is. Right? There's these kind of small spots on it, and those spots are generally bigger than the Earth. So in these images, the sunspots appear darker, but that's only really in comparison to the very bright surroundings. If you had one of these sunspots, somehow I want to take it away from the sun and put it up in the sky, it would still be very bright. As I mentioned before, on average the photosphere's temperature is about 5,800 Kelvin. These sunspots are a bit cooler, about 2,000 degrees cooler in fact. Taking a little bit closer look then at some images of the photosphere, well, in the upper left in A, just have another image of a sunspot. But if you get real close to some of these sunspots, they have some interesting kind of structure. I don't know, kind of looks a little gruesome actually to me. But just to keep an idea of the scale on here, there's about the size of a continental United States on there. And so those dark areas have these sort of like hair or like line things coming out of them. And then around them, you can start to see these like little islands sort of looking thing, or scales almost. And if we just look at some of those, that's an image on the bottom left. That's what we call granules. And the sun's photosphere is just covered in these granules. If you think back, underneath the photosphere is what we're calling the convection zone. And convection is, well, an example of convection is like when you're heating up a pot of water or like a soup. You're heating up the very bottom of it, and that heat is eventually being brought up to the surface because the bottom stuff gets hot and the hot stuff wants to rise, and eventually it rises to the surface and kind of bubbles up, right? And then it kind of cools off and will come back down and get heated up again, and you get this sort of pattern going on. The hot stuff is rising and then cooling and falling and then heating and then rising and then cooling and falling. So if you think about the surface of like a boiling soup, you might actually see something very similar to that image. It's a continuous pattern of these granules that go on the surface of the sun, in the photosphere. So the average size of one of those little granules is about the size of Texas. They typically last for only a few minutes, 5 to 10 minutes, and the largest could be as large as the size of Earth and last for a whole day. We'll come back to those sunspots a bit later. But for now, let's move on to the next layer of the sun's atmosphere, the chromosphere. Now, there's not a whole lot the book says about the chromosphere, and I'm not terribly familiar, so yeah, there you go. These are some images of the chromosphere. The one on the right is similar to the first image that I showed you, where you put a dark, opaque disk in front of the sun, so you cover up all the sun, and you can see a bit better the atmosphere, the very edge of the sun. And you can see in this image, it's a bit red. It's a little bit on the red side. The image on the left is a full image of the chromosphere, but it's taken not in visible, because we wouldn't see it in the visible range. It gets blinded by the photosphere. If you look at the emission of this particular line of hydrogen, particular hydrogen emission line, then it's very strong in the chromosphere, and so you can get an image or a picture of the chromosphere just looking at that part, very specific part of the electromagnetic spectrum, this hydrogen alpha line. Maybe we point out too that this process of like putting a disk in front of the sun in order to see sort of the outsides of the sun happens during an eclipse. So if you've ever seen a full solar eclipse, and you might have already seen an image sort of like this, and that edge of the sun, you start to see a lot more of the atmosphere of the sun when the moon goes and blocks most of it. And so that stuff was always there. You just don't see it. And it's kind of like if someone was shining a spotlight at you and somebody else came along and tried to shine like a flashlight on you at the same time. It's like you're not going to see the flashlight at all, right? The spotlight is so much brighter, it just blows out whatever the flashlight's trying to do. So similarly for the sun, the photosphere is incredibly bright, and so we're kind of blinded to all the other stuff that is there unless we are a little bit clever and look at particular emission lines or particular parts of the electromagnetic spectrum that the photosphere is not emitting. Typically, the other parts like the UV, the extreme UV, and X-ray. There's an interesting fact that helium, the element helium, got its name from the chromosphere in a way. So people were observing the chromosphere, and they observed a particular emission line from the chromosphere, the yellowish line, I believe. And if you didn't know, Helios is the root word there, and I think it's Greek, that means sun. So they named that emission line helium, and it was only later, 30 years later or so, that that same line and that same element then was spotted on Earth, or was observed on Earth. So eventually it turned out that that was coming from the element that we now call helium. So we talked a little bit about the photosphere, which is kind of like the surface almost of the sun. Then after that we get to the chromosphere, and in this chart we're seeing a bit about the temperatures of those different areas. So the photosphere is a bit hotter than the chromosphere, but the temperature tends to kind of drop down a little bit as you get towards the chromosphere, and then picks back up a little bit. And as I mentioned before, the corona, the very most outer region of the sun's atmosphere, is actually surprisingly hot, very hot. So after you get above the chromosphere, we get to this transition region between the chromosphere and the corona. You're sort of transitioning into the corona. And it turns out that the temperature jumps up. It's real hot. So we go from a few thousand Kelvin over the span of about 1,000 kilometers, we're up to something like a million or a few million Kelvin. Alright, so now we're finally out to the outermost region of the sun's atmosphere, which we call the corona. On the left, we have another image using this occulting disk to block out the main visible light from the sun, and we can see some of that outer atmosphere. These parts of the corona. This is sort of like jets of energy streaming out from the corona. And these images are, I think, somewhere in like the transition region and into the corona. And so they're taken in the extreme ultraviolet range. So if you remember, we have visible light, and then even shorter wavelengths than visible light, even higher energy wavelengths, are ultraviolet, and beyond ultraviolet is X-ray. And so once you get to very, very short ultraviolet, like this very small wavelength end of the ultraviolet part of the spectrum, that's what we start to call the extreme ultraviolet. It's like almost to the X-ray region. So like the Earth's atmosphere, it sort of gets less and less dense as it gets further away, or as we get further away from the surface. Same thing sort of here, the corona, we're pretty far away from the surface of the sun, and it's a fairly low density area. I don't know, maybe it's just me. I think some of these images from the corona, we'll see more of them, and so the activity in this area of the sun's atmosphere is just some of the coolest looking stuff. I don't know, it really gets me. In the animated image here, like all this activity, see like these loops forming and growing and shrinking, these areas getting much, much brighter, letting out some radiation or something like that. Yeah, pretty wild. A little bit more about the corona. Again, it's the outermost region of the sun, and the way we define it, it extends very, very far. Technically, the Earth is within the sun's corona. Yeah, like I said, very low density, like 1 trillion times less than the photosphere. Generally, it's very hot. Generally meaning, you know, kind of on average. There are areas and like clouds almost in the corona that are much cooler. In general, quite hot, like 1,000,000 degrees Kelvin. Some things that we see when we look at the corona are these coronal holes. So in the image on the bottom there, there's sort of dark region, right? And that's sort of like an opening in the corona. And it's a relatively cooler region of the corona. As it turns out, a lot of the stuff that's happening in the sun's atmosphere is driven by magnetic fields. And we'll talk a little bit more about that as well, I think in a couple of slides. But for now, just to say that these coronal holes are generally places where the magnetic field is kind of like burst open in a way, it's loose. And from these regions is where we get a lot of what I've described to you before as the solar winds. So this is material that just kind of like streams out of the sun on a regular basis, just doing it pretty much all the time, more or less depending on how large or how many of these coronal holes there are. It seems like mostly where the solar winds are coming from. And just to remind you, those solar winds are pretty much made up of protons and electrons. They're moving quite fast, something like 10 to the 6th, a million miles per hour. And a proton and electron, very, very small things. But the sun is putting out tons of them all the time. And so over the period of a year, it can lose like millions of tons of its mass through this solar winds. They're pushing out these electrons and protons. A million tons sounds like a lot, but to the sun, it's nothing. It's like a hair that just dropped off my hand here, right? Insignificant to the mass of my body. So let's get back to these sunspots. Look at what happens around them, above them, and yeah, think about stuff like that. So the image here is just kind of cool. You can see a sunspot sort of form and the sun also revolving. So in the far left, it's like one day, and then the next day, the next day, the next day. And so it starts out fairly small, but you can see by, say, the 27th there, those sunspots have grown quite a bit, and then maybe they're getting a little bit smaller. Right? This is the sun just revolving around two of us at the same time. I mentioned a couple of these things already, but definitely want to point out that these spots we have found go along with the amount of magnetic field activity. Right? So how much change there is in the sun's magnetic field, how strong or weak is it, and unlike the Earth, which sort of has this overall magnetic field, right? It kind of comes out of the North Pole and it goes in the South Pole, fairly uniform over the whole Earth. The sun has tons of magnetic field activity going on. It's not nearly as clean cut as that. There are like North Poles and South Poles like all over the place on the sun. So there's magnetic fields that come out and loop back in, and come out and loop back in all kinds of different places. It's quite complicated. But what we've seen is that these sunspots are sort of harbingers or go along with higher magnetic field activity. And also, as pointed out here, I think we'll come back to in a minute, they also seem to go along with things like solar flares and coronal mass ejections. Flares being like a bunch of electromagnetic radiation suddenly streaming out of the sun. Coronal mass ejections is like huge masses of material pushed away from the sun. We'll get back to this. So on the photosphere, right, that's the most visible part of the sun that we see when we look at it. And those sunspots are some of the only like major features that we make out. You know, on the very small scale or much smaller scale, there's those granules, but the sunspots are much larger and they're easier to make out. And it turns out people have been observing sunspots on the sun for quite a while. Right? You don't even necessarily need a good telescope to do it. It's not until much more recently that we've been able to look at other parts of the electromagnetic spectrum, like not just visible light, but particularly like ultraviolet light and extreme ultraviolet light, that we could see other parts of the sun's atmosphere, you know, like the chromosphere and the corona, and see that there's all this activity going on above these sunspots. So the images along the top and also in here are looking at the sun at particular wavelengths in the electromagnetic spectrum. I'm not going to get too much into it, but the one on the far left is probably close to an X-ray part of the spectrum. The two middle here are somewhere in the UV. Skip over this one for now. And then you have some other images down here which are also probably in, well, the photosphere is in the upper left there. You can see the sunspots. Then in this green upper right image, out a little bit further, maybe this is like the chromosphere or like the transition region. And then even further out, looking at things happening in the corona. But overall, like if you look between the photosphere and then in that sort of chromosphere image, sort of orange one and then the green one here, we can see this alignment with where the sunspot is in this very bright region in that image, right? So that very bright region is probably stuff streaming out of the sun, probably electromagnetic radiation. The overall picture here then is that where the sunspots are is aligning with all the other images where there's activity going on. And I guess to say that in the upper right one here, it's actually of the sun's magnetic field activity on the photosphere. So that dark area is actually a sunspot. Right? And you can see it goes along with that really intense area and all these other parts of the atmosphere, sun's atmosphere. So just to reiterate again, that we think that what is driving these sunspots and all this activity above the sunspots are magnetic fields that are generated within the sun, and probably in the convection zone where, like I said, it's like that boiling sort of soup, really, really hot gas that's sort of coming up and then dropping down and coming up and dropping down. And that soup is made up mostly of electrons and protons, so these charged particles, these electrically charged things. And when you have electrically charged things moving around, that's how you make magnetic fields. Just to emphasize, though, that magnetic fields here we're talking about are incredibly strong. You know, if you ever play with a bar magnet or like even a very strong magnet, like a neodymium magnet or something, that is nothing compared to what's going on in the sun. So here we just have an attempt at least to give you an idea of how magnetic fields, along with the rotation of the sun, might end up with these sunspots, these sort of holes in the sun's surface in a way. So if we think about a sort of normal, like, planetary magnetic field, it is sort of going through the center of the planet, or like the sun in this case. We start out thinking about the far left there. We have this fairly nice uniform magnetic field going up through the surface, and then it would kind of come back around, move back around way outside. So if we think about starting there, but the sun then is rotating, and as I told you, the different latitudes of the sun, or the different parts of the sun's surface, are rotating at different rates. And the equator tends to rotate a bit faster than the areas towards the poles. So this whole thing is rotating, but the middle is rotating faster. So we move along in time a little bit, and those magnetic field lines sort of get dragged along with this material, and we get to this point where we have the magnetic field coming out of the top here, but it's getting sort of bent to one side. It's getting folded around there. So what happens then is eventually you drag these sort of fields along enough. Well, you can think about it as like snapping of like a rubber band or something, right? You pull it enough, and finally it snaps. But the thing with magnetic fields is they don't like being free and loose. So when they snap, they sort of end up looping back around right away and catching on themselves. And so these holes, or these loops in the lines now, are where a magnetic field line has sort of like snapped and then looped back on itself. And the idea then is those holes are sort of where we end up with these sunspots. Hopefully that makes sense. I mean, this is even still a simplified sort of picture of what we think is going on, but it still can be a tricky thing to grasp. So talking a lot about magnetic fields, I want to give you some idea of like how we know about the magnetic fields on the sun. We can't really go there with like a compass or like another magnet and see how much it pulls on it. It's not very practical. Luckily, there is a certain effect that happens to gases or to atoms in general when they're in very strong magnetic fields. It goes a little something like this. We think back to when I was telling about the spectrum or spectra of light and how we analyze spectra. One thing that we do is we pass light through something like a prism, and the prism ends up spreading that light out. And so on the other side, we look in, white light goes in. That white light is made up of these different wavelengths, and by going through the prism, it spreads those wavelengths out. And so on the other side, we get to see the different colors because they've been spread out like that. So a prism will bend the light as it comes through. And if you recall, I told you that different wavelengths bend different amounts. So the violet bends the most, so it hits the prism and bends down. Red bends the least, so it hits the prism and bends down, just not as much. So then when they exit, the violet's coming way down here, the red is up here. So try to think about then like a container of some gas that is really hot, so it's glowing, it's emitting light, right? It's just coming from the gas itself. And if we can imagine a gas that's doing that, and it's only emitting one color, right? One specific wavelength of light. Say like this turquoise sort of color. If it's only emitting that one wavelength, we could pass that light through a prism. It's going to bend, but there's no other wavelengths to spread from, right? It bends a certain amount, it bends again when it goes out the other side. It's just one wavelength. It's still the same. Now though, if we take that gas, that really hot gas that's emitting light, and we put it in a very strong magnetic field. I just threw a little bar magnet thing up there. It indicates a magnetic field, really very strong magnetic field. It turns out that that light that's coming out, you might not see it before we pass it through a prism, before we spread it out. But that light now has split from that single wavelength in the tube. So if we were to pass it through a prism, that turquoise light might spread out, and on the other side we would now see like a green and a blue. So this is just something that atoms do, and the way we explain it has to do with quantum physics and something called intrinsic spin. We're not going to get into all of that, just to say that they do. That's what happens. And beyond that, the amount that they'll split, or the amount of difference that we'll get in the resulting wavelengths, is proportional to the strength of the magnetic field that gas is in. So a very strong magnetic field, these wavelengths are going to split more. In this case, splitting more would mean that you're pushing the wavelengths even further from that turquoise, so we might end up with like a violet and an orange. You're getting further and further away from that initial wavelength. This is known as the Zeeman effect. So if we look at a particular wavelength that a gas that we know is on the surface of the sun that's emitting, say like hydrogen, I think in actuality we typically use a particular wavelength of calcium that's in the sun's atmosphere. I think so. But anyway, we look at a particular emission line from an atom, and if it's in a strong magnetic field, that line that we know is there will have split into two lines. And again, the amount that it splits depends on the strength of the magnetic field. So by looking at the emission from this element at different places all over the sun and seeing how much that line has split, we can say how strong the magnetic field is or weak it is all over the surface of the sun, and we could build a picture of the magnetic field along the surface of the sun, all over the surface of the sun. When we do that, we make what's called a magnetogram. So on the left there is actually an animated picture, so many of these sort of images of the sun, watching it as it revolves, and the dark and light areas are both indicating strong magnetic fields on the surface of the sun. The white versus black is basically like a north versus a south pole, but we don't need to worry about that too much. The important part is that we can map out the magnetic field over the surface of the sun. And again, that goes along with those sunspots that we see in the visible spectrum on the photosphere. So what does all this tell us? Well, if we look at this activity on the surface of the sun, right, the sunspots that go along with these magnetic fields, that go along with the other activity above the sunspots, we've seen that there is a cycle to them, right? There is periods where there's a lot of sunspots, there's a lot of activity on the surface of the sun, so strong magnetic fields happening all over the place. And there's periods where it's weaker. There's much less sunspots. And so this image on the right here is the sun, well, particularly the magnetic field on the surface of the sun being shown throughout a period of like 7.5 years. So we go from the left, bottom left is the first image, and there's a lot of magnetic field activity on the surface, right? A lot of strong magnetic fields going on there, just indicated by how much black and white areas there are. And you move around, you start to notice that all that magnetic field activity is sort of dying down. Dies down, dies down, dies down, and then all the way in the back, there's almost no black and white areas. And again, there's very little of this like magnetic field activity going on. Keep going along, that activity starts to increase again. So this sequence was taken over about 7.5 years. It's starting at about a maximum and not quite making it back to a maximum, so maximum to minimum and then back to a maximum again. The full cycle we've seen takes something like 11 years on average. It could be less, it could be more, it could be like 9 years. We've seen it take up to like 14 years. But on average, the sun goes through this like maximum to minimum, back to maximum in about 11 years. This is what we call the solar cycle. Overall, the energy output of the sun varies over this cycle, but it only varies by like 0.1%, so not very much. And in the upper image here, we see another version or another way of looking at this cycle. This one, I believe, is probably looking at part of the corona or maybe the transition region. So those are probably like extreme ultraviolet images. But if you start up at the top, on the left-hand side there, we got 1996, and about every year in another image, and you can just see visually this increasing amount of activity. Right? We're going from almost a smooth, like single color-ish in 1996 to all these areas where just stuff's happening. And the color is indicating the temperature, but probably it's also a good indication of like magnetic field activity. So we go all the way to 2001, it says peak, and then it starts to go back down again. The overall activity is going back down, and we get to 2006, almost back to a minimum again, right? So that was about 10 years. Like I said, on average, it's about 11 years. If we look at the number of sunspots throughout this cycle, well, it can be as few as none at the minimum, usually still like a couple, but sometimes as little as 0 sunspots overall, to a maximum of like 100. Right? I think generally in a maximum there's like a couple dozen, but we've seen maximums that are really intense and like 100 sunspots over the surface. Even still, that's a very small area of the sun's surface, but it's a lot of sunspots, so a lot of activity. So I told you a decent amount now about like the sunspots and the magnetic fields that are around those sunspots. That's all in the photosphere, and we said a little bit about the upper regions like the Chromosphere and the Corona. I'm just going to tell you a little bit now about the names that we give to some of the bigger things or prominent things that happen in those parts of the sun's atmosphere. So for one, there are these things called prominences, or a solar prominence, and the upper image here is sort of a collage of 4 different images of the sun, but there's prominences in all of these images. Visually, they're just kind of these big loops of stuff around the sun in the far reaches sort of the atmosphere of the sun. So again, like neither of these images are visible light. You wouldn't see this looking at the sun. You might see some of these prominences a bit actually during an eclipse, right? Because there is some visible light that Corona is emitting, so you could see some of that stuff. But for the most part, remember the photosphere is just blinding us from seeing anything else in the sun's atmosphere. So these prominences are made out of plasma, which is just electrically charged gas, in a way, very hot electrically charged gas, sort of like that soup of like protons and electrons. And they tend to form these loops, right? And the loops will sort of like grow and then eventually shrink. Most of the time these prominences are kind of grow and then they're stable for a little while. They wiggle around, but eventually they kind of shrink back down into the sun. Besides the prominences, there are things called solar flares, which is an eruption of electromagnetic energy in the sun's atmosphere. So almost think of like a volcanic eruption, but instead of spewing out like lava and things like that, it's just spewing out really intense electromagnetic radiation. So that's why when you look down here, some of these really bright spots, particularly in the upper right there, is a flare. And we're looking at like an ultraviolet or extreme ultraviolet image already. And the fact that it's super bright still means that that radiation is even more energetic than this part of the spectrum. So maybe X-rays or something, but like very high energetic electromagnetic radiation. All of these things, again, they tend to coincide with sunspots. The exact way that they're connected or the one causes the other, it's not very well understood. But these things can happen together. But the most sort of like violent activity on the sun, or in the sun's atmosphere at least, can also happen along with the prominence or a flare. That's what we call a coronal mass ejection. I mentioned this earlier, but this coronal mass ejection is essentially just a mass of material that the sun like spurts out. Or big old blob of very hot gas, mostly protons and electrons still, but just shot out from the sun, right? So rather than the solar flares, which is purely electromagnetic radiation, this is actually sort of like part of the sun, matter, material coming from the sun. Again, I find these images just fascinating. I think they're incredible. And we got a really cool video that shows some coronal mass ejections. So let's watch that. So you kind of got this like filament building up, and then something happens and it just jets off into space. Oof. Oh, so you see the whole sun, and then there's the ejection. Decent amount of activity going on here. I think coronal mass ejections are mostly going to happen like around sort of a solar maximum. Oh my gosh. It reminds me of something, but I can't put my finger on it. Right, so you're moving out further and further, looking at seeing this sort of ejection and stuff coming. So as you might imagine, if that stuff comes towards us, towards Earth, it can cause some problems. And in fact, the solar wind itself can also affect, and does affect regularly, the Earth. So the solar wind, remember, is just a sort of like normal-ish stream of electrons and protons, mostly electrons and protons, from the coronal holes that form in the sun's atmosphere. These coronal mass ejections is sort of like massive end of that stuff. This is build up of these, generally these sort of like loops, these filaments that just burst and then shoot off into space. And all this stuff is electrically charged. So before, something like a few hundred years ago, before we had really developed our usage of electricity and technologies, this stuff, it might have caused some interesting things visually, but it probably wouldn't have affected us that much. However, we rely very heavily on electricity, the flow of current, and beyond that, we rely pretty heavily on these things that we've shot into space that are orbiting Earth, satellites. All this stuff can affect those things. So the solar winds and the coronal mass ejections together is sort of what we've termed space weather, though I think solar weather might be a better term. That might just be my opinion though. So what are the kinds of things that can happen? Well, the solar winds, not quite as detrimental in general, but they can lead to a buildup of static charge on satellites and even, spacecraft in general, like the International Space Station. And if you've ever drug your socks across a carpet on a dry winter day and then touch something metal, you get a little shock. That might not seem like that much, but that's actually quite a lot of electrical charge that's jumping across from you to the metal. And that's due to an electrostatic charge that's being built up. So that same kind of buildup can happen on satellites because of the solar wind. And when it discharges, it can cause some significant problems for electronics on board. That's just the solar winds. The coronal mass ejections can do some fairly significant things. For one, they can literally heat up the upper atmosphere. And if you heat something up, it tends to want to expand. Right? So the upper atmosphere expands a bit. And the thing is, a lot of these satellites are orbiting like just outside of the atmosphere, or like at sort of the very edge of the upper atmosphere. But if that atmosphere expands a bit, then they start running into the atmosphere. That running into causes some drag, which means that they're no longer going to continue to orbit nicely. They're going to start to lose altitude. Very big problem. If you don't have thrusters on a satellite, then eventually that means that it's just going to continue losing altitude and losing energy. And it's going to burn up in the atmosphere or crash land somewhere. Not good. The coronal mass ejections in general are just going to be increased amount of radiation that astronauts are going to be exposed to. Even increases the amount of radiation in general that you would experience everywhere in a plane and a few thousand feet up, but even on the Earth's surface. And in fact, these coronal mass ejections sometimes can be so strong if they're aimed at the Earth at all, then they can cause surges in power lines, which can blow out transformers and can affect our electrical grid. And if you didn't know, our modern life depends quite a lot on something we call Global Positioning System, or GPS. And that system is built off of a large network of satellites orbiting the Earth. So all these things can affect satellites, right, which can affect our GPS, which can cause a lot of problems because we rely on it for all kinds of things, for trade, for travel. So all that is to say that this thing that we call space weather, it's been decided that we should be monitoring it, and we even now have sort of organizations or things within organizations that monitor the space weather. Right? So this is just a screenshot I took of the Space Weather Prediction Center's homepage. And it has all these like predictions for different kinds of space weather. I'm not even really sure what a lot of them actually are, but along the top there's these different labels, and I'm assuming that they change color and change letter depending on the severity or the expected severity of incidents, space weather. And so just like a normal weather report would be, it's like, is it going to rain? Like, how much is it going to rain? This is like, how intense are the solar winds going to be? Do we have to worry about astronauts going on a spacewalk? Right? These are things that you might get from this sort of space weather report. This actually falls within NOAA, under the umbrella of NOAA, which is the National Oceanic and Atmospheric Administration. It does a lot of predictions of weather forecasts, hurricane forecasts, tornado forecasts. Very useful sort of thing. So I said all this stuff that can cause problems. The space weather can be a problem, all these solar winds, coronal mass ejections. Just to say too that there's some kind of nice things, particularly the auroras. I think I mentioned before that the aurora borealis and the aurora australis in the North and South Pole is a result of material that's impacting Earth's atmosphere, but it's electrically charged material, and so it gets kind of pulled along and directed by the Earth's magnetic field, sort of winds around until it comes into the pole, where the Earth's magnetic field comes in, and crashes into the atmosphere, excites or energizes some of the gas in the upper atmosphere, and then when that gas de-excites, or lets go of that energy, it lets it go, a lot of it, in the form of visible light. So we get these cool auroras. Very nice things. Well, that is it for the first lecture about our local star, the Sun. Next time we'll talk a bit more about the processes driving the Sun and give you an idea of what we think is going on inside. I will see you later.